Dream to become the next Sir Isaac Newton or Albert Einstein? Learn from the master. Refath Bari. Watch his videos to achieve your dream. Subscribe.
Welcome to Linear Algebra lecture number 87. Today I'm excited, very excited to present to you A equals LU factorization. Let's hope you didn't hear that, alright? That was... Alright, let's not...
What was that propagation of methane?
It's alright, folks. Remember, the best way to stop global warming is to learn linear algebra. Now, today we're going to be discussing A equals LU factorization, alright? Now, most likely, my YouTube viewers and my Facebook viewers, you've probably never heard of this before, have you? And you probably never will. But the fact of the matter is that A equals LU
then
factorization...
why are we learning this right now?
Well, the reason is because every single computer in the world depends on A equals LU factorization. Why? Well, try to think of one example. Google, for example, please. Student, please finish your homework because you will be required to hand them in by the end of the lecture. Otherwise, you will be, you'll be forced to walk in front of the class. Now,
Oh no.
please, can we finish the lecture now, the homework? Now, back to the key idea of why do we need A equals LU factorization. The reason why we need it is because, think about Google. Google uses the PageRank algorithm to list websites in chronological order when you search something up. Now, to do so, Google relies on hundreds of matrices that it will probably never disclose to the public. But the fact of the matter is that all of these algorithms depend on matrices. And to decode these matrices easily, you need A equals LU factorization, alright? Now, let's go ahead and get started, alright? Facebook and YouTube. Student, you'll be required to show your homework to the audience by the end of the lecture, so make sure you have it ready, okay? I want the full proof. Okay. Now, I want to start with a very easy, simple idea, okay? What does A equal LU even mean, right? I mean, the first thing you learn when you see a new word is what does it mean, right? Same thing same idea when it comes to matrix factorization, right? What does A equals LU mean? All right, that's the first thing we're going to tackle, okay? So to tackle that question, I've got my big fat box of markers. It actually quite literally says markers over here. So, have no doubt this really is a box of markers. Now, the first and foremost thing I'm going to do is try to explain this idea of A equals LU factorization, alright? So let me go ahead and write it down. Student, why are you not completing your homework?
I will need another variety of marker.
Sure. Grab as you please. Let's not take that phrase out of context. Now. Do we have a question? What question do we have from the live audience? A plus 1 over A equals 2. What is the accurate value of A to the 4th plus 1 over A to the 4th? Alright? We're going to answer that question after we understand A equals LU factorization. Alright? I'm going to entertain the viewers with that question a little bit. But first, let me explain A equals LU factorization. Thank you for the question, Nasima Badoom. Alright? Now, what is A equals LU factorization? To understand it, we must understand what A represents. Alright, student, make sure you also use the second page of notes. A represents a matrix, right? So let me go ahead and denote that. A represents a matrix. So I'm going to write it down. A is a matrix, and through elimination, through the process of elimination, okay, we're going to take A and transform it, turn it into a different matrix, and that matrix is going to be U. Alright, so through the process of elimination, A is going to become U. Now you're probably wondering, why do we call it U instead of any other letter? Well, U simply represents the upper triangular matrix, right? And
I thought it would represent potential energy.
very funny. Upper triangular matrices are really the ideal kind of matrices because, they're easy for computers to understand and process and read. Alright? So this over here is the upper triangular matrix. Upper triangular matrix. Alright, hopefully that makes sense. Now that we understand what A is and what U is, we're ready to understand what L is, right? Because L is really the kind of skeleton, the backbone. It's kind of the spine of all this, of this entire algorithm, okay? So L is gonna come in the middle over here, and you know what takes us from A to U? A to U, we get from A to U with elimination. Right? Gaussian elimination, to be more specific. Gaussian. I mean, there's many types of elimination. Carl, Jordan, there's many types of elimination,
Okay,
but
then.
really the fact of the matter is we're using Gaussian elimination to get from A to U, right? But then how do we get back? How do we undo that? How do we get from U? How do we get from U to A? Is it like a magic key that I have to turn? Say the magic word, please? No. The fact of the matter is that there's a magic matrix, and it's actually called L. Right? So this is almost like a function, right? This is almost like how a function works. A function and its inverse, right? So let's try to understand this process a bit better. Let me clarify what's going on here.
I finished my homework.
All right, student, you will have to hand it in for consideration at the end of the lecture. Not now, but at the end. Anyway.
I will just hand it in below here.
Thank you. Okay. Why did you hand it in there, student? Okay. Now,
Now can I take a little online test?
to get from A to U, we need Gaussian elimination. To get back from U to A, we need L, the lower triangular matrix. All right, so let me go ahead and write that down. L stands for the lower triangular matrix. Lower triangular matrix. All right, and now you can kind of.
I need Wi-Fi.
Yes, some of us also need some common sense. Now,
I really need Wi-Fi.
we can't provide free Wi-Fi at this mathematics hotel, so please.
This is a hotel?
To get from A to U, to get from the matrix A, any general square matrix A, to U, I'm going to need the Gaussian elimination, right? But to get back from U to A, to get back from my upper triangular matrix to my original square matrix of order n by n, I'm going to need the lower triangular L. Alright, so just to give you a kind of schematic to understand this process, you can start by taking a look at this picture. Okay, instead of A, what I'm going to draw is just some random matrix. And folks, if you have any questions or comments that are math related, go ahead and leave them below. I'll answer them at the end of this lecture. Now, let's say we have a matrix A, right? And hopefully you remember how to denote the entries in a matrix. Alright, so the entries of a matrix are simply, I'm using this as a square matrix of order 2, but this extends to any square matrix, right? Hopefully you get that idea. But basically this is A sub 1, 1. Why? This is the first row, first column. That's why I have A 1, 1. First row, second column. Second row, first column. Second row, second column. Alright, so hopefully that's understood. Now. We're going to take this matrix, and to get to my upper triangular matrix, I'm going to need some Gaussian elimination, alright? So, to show you what an upper triangular matrix looks like, I'm going to use a schematic, alright? A schematic. So a schematic, for those of you who don't know, is just a visual demonstration of what my upper triangular matrix is going to look like. So, just like any matrix, really, my upper triangular matrix is simply going to be as follows, okay? So it's going to look like
The Wi-Fi here is horrible.
all the matrix entries below that diagonal are going to be 0. So I'm going to represent that with a big fat 0. And all the quantities above the diagonal are going to be non-zero entities, alright? So I can go ahead and just write this as B1, 2. And of course along the diagonal, it also has to be non-zero quantities, alright?
Finally.
So I can go ahead and denote this as B11, B22, and this, for example, would be one example of an upper triangular matrix. What about lower triangular? What does lower triangular matrix look like? Well, a lower triangular matrix is simply going to be as follows, right? Instead of the upper triangular, we're simply going to have all the entities above the diagonal be 0. So that's going to look something like this, right? All of those quantities are 0, and then any entity below the diagonal is simply going to be non-zero, or on the diagonal, I should rather say. So for example, d sub 1, 1, d sub 2, 1, d sub 2, 2, all of these will be non-zero quantities, Give me a hands up if you understand that. All right, so hopefully that has been an in-depth explanation of A equals LU factorization. Let me move this a bit for our YouTube audience. Now, we are ready to handle the audience questions, all right? So if the audience has any questions, now is the time. Yes, okay, good job, Mr. Maltram Twinbox. It is the opposite of upper, okay? That's the whole point of calling it a lower triangular matrix, okay? So it's kind of like attaching puzzle pieces. You take an upper triangular matrix and a lower triangular matrix, you combine them, you get the general square matrix A, okay? Alright, so hopefully that's been an enjoyable lecture on the A equals LU factorization, and we'll see you next time.
Subscribe to Bari Science Lab to fall in love with math and science, especially programming.